This product video showcases one of the latest innovations from 2.6. To start though, I'd like to give you a brief introduction to 2.6, starting with our name, which refers to groups 2 and 6 of the periodic table of elements. By chemically combining elements from these two groups, 2.6 produced some infrared optical crystalline compounds, like cadmium telluride, zinc selenide, zinc sulfide, and so on. The company name was actually chosen as an homage to these compounds, which are commonly referred to as 2.6 materials, and which were our first business and core expertise. We are a vertically integrated company, and we serve all levels of the value chain, from engineered materials to components, devices, and subsystems. 2.6 was founded in 1971, and since then, we've grown significantly and today can count more than 22,000 employees in 75 locations through 18 different countries. We can say we are really a global company. And we expanded our business as well. Our core competencies remain engineered materials and optoelectronic devices, starting from which we can build solutions for several different markets and applications, including industrial, semiconductor equipment, consumer electronics, automotive, life sciences, wireless, and optical communications. And optical communication is exactly the topic of today's presentation. So let's start. As you saw from the title, I'm going to talk to you about poles. Okay, great. But what does this strange name really mean? POLS is the acronym for Pluggable Optical Line System, which is a new platform we've developed at 2.6 for the 400G ecosystem. But let's take one step back, starting from the market trends that lie behind the emergence of DCI and the adoption of 400ZR. We are living in a world where everything is or going to be connected, transmitting plenty of data that goes somewhere, data that are stored, processed, and analyzed. The number of connected devices is expected to reach 500 billion by 2030, which will be about 59 times larger than the expected world population of 8.5 billion by that time. Megatrends like 5G, artificial intelligence, the increased number of people connected to the web, the growing importance of mobile communications as a social infrastructure, the work and learn from home trend driven by the pandemic we're now experiencing, the Internet of Things, the need for broadband access, and better connection performances generate a huge amount of data that need to be transmitted and stored. It is estimated that per every gigabyte entering a data center, 10 gigabytes are transported. You have to think that each time you pick up your phone without making any call, but yet open an app or navigate on the web, that you are entering a data center. So we can imagine the enormous amount of traffic generated intra and inter data center. The data center IP traffic grows fast. Cisco estimated that in 2021, which is next year, it will reach roughly 21 zettabytes, triple with regards to where it was in 2016. The amount of so-called north-south traffic from the data center to the user is only a small part of the overall quantity and is actually less than 15%. The majority of traffic, roughly 85%, is so-called east-west traffic, which remains within the data center or goes between data centers. The latter distinction is becoming a little bit blurry. With the advent of the distributed architecture, the boundaries between a distributed campus and a cluster of individual data centers tend to overlap. So we can consider that the DCI application is actually an area across intra-DC and DC to DC traffic as represented by the light blue circle. Focusing now on data center interconnect, we can see that the DCI IP traffic will grow at a CAGR of 32% and will grow across all the industry verticals. If we look at the distances, the majority of the investments will be on metro links, which represent about 56% of the overall DCI market and include, in the chart at the bottom right, both the edge and the core metro networks. We saw in the previous slide the emergence of DCI and its drivers. But what will be used in DCI links in terms of optics? The answer is DWDM to cover long distances and to enable high capacity. If we look at the DWDM transceiver sales by segment, we can notice that the cloud application is increasing. The pie itself is increasing, but the cloud has gained market share at the expense of telecom. And the accumulated bandwidth calculated on the DWDM transceiver sales forecast is expected to continue growing in the next years, especially in the cloud. Within the many types of DWDM options, 400ZR is emerging as the most interesting solution. Why? Because it will support up to 100-kilometer distance and high capacity, and is also standardized with all that goes with that. Modules will be multi-vendor, interoperable, and cost-effective thanks to the strong competition among the vendors themselves. But 400ZR is coherent. And what does coherent remind you? Well, with respect to a data center network, you would tend to think of coherent and DWDM as a complex technology, typically used in high-performance, high-cost, long connections. And generally speaking, coherent is not that easy to be installed and configured compared to the typical point-to-point gray optics often used inside a data center. 400ZR is instead a pluggable, coherent solution able to make DWDM for DCI as simple as intra-data center optics. So point-to-point without ROADMs, without the need for inline amplification, but still colored without aggregation and amplification at the edges. Here we can see the scheme of a typical DCI DWDM link. At both edges, there is a switch populated with gray client signals going into a transponder from which some colored DWDM channels are generated. They are then optically aggregated by a multiplexer, amplified by a booster amplifier, and then launched into the fiber. On the other side, the process is the inverse. The DWDM channels are amplified by a preamp, demultiplexed, and then they go into a transponder. From here, the client signals are connected to the switch. The 400ZR collapses the transponder functions into a pluggable module that can be directly inserted into the switch. You won't need the transponder any longer, and you can connect the 400ZR optical output to the line system. It's simple to be managed, multi-vendor, interoperable, just like the gray optics are. Fantastic, but one piece of the puzzle is still missing. We haven't talked about a dedicated optical line system. In a traditional DWDM system, mux, demux, and amplification at the transmitter and at the receiver side of the link are managed by dedicated optical line systems, which can be bulky pizza boxes or line cards in a rack, depending on the specific equipment used. Poles is the answer to revolutionize this traditional approach. It integrates the key elements of an optical transport system into a pluggable module in an OSFP footprint, exactly like the 400ZR transceiver does for the generation and detection of coherent signals. 400ZR outputs can be connected to the poles, and the poles can then plug directly into the same switch. With such a solution, you save not only space, but you can decrease your power consumption, reduce cost, and make the installation as easy as it is with gray optics. You can see its picture. It's the world's first pluggable optical line system in a compact OSFP module, the same as one of the 400ZR transceivers. In this slide, courtesy of Arista, you can see a complete setup that was already proven. The poles module is what you see defined as the OSFP-LS, developed in collaboration with Arista. It's been qualified and is compatible with Arista switches. It includes compact bidirectional optical amplifiers, both preamp and booster, together with a MUX/DMUX, and can be directly plugged into an OSFP transceiver slot on the switch. Auto provisioning manages link configuration and laser safety. The module supports up to 8 DWDM wavelengths on a single fiber pair to deliver up to 3.2 terabytes of data center traffic over 100 kilometers when used in conjunction with the new generation of 400G ZR digital coherent optics. We can see two switches separated by a 120 kilometer span. The white pull tabs are the 400G ZR modules. The green ones are other pluggables in the rack. The black pull tab is the OSFP-LS. Only one slot of the switch is taken. 8 ports as transponders and 1 is the line system. The 400ZR is tuned to any one of 8 wavelengths, and this is the only thing you have to care about. The MUX/DMUX pair is completely colorless. When installers do not have great experience in DWDM, or perhaps weren't trained for DWDM, even connecting coherent channels to a MUX is not obvious. Is it the right polarity, the right channel to the right port, and then in the amplifiers? Which is the preamp, which is the booster? Having in mind this kind of constraint, the combination of 400ZR and poles makes deployment easy, just like other gray optics. The optical scheme you saw in the previous slide is the real setup of a demo that Arista showed in a video they published in June. An Arista switch was populated with 8 400ZR transceivers, tuned to 8 different wavelengths. Their outputs were aggregated through a colorless MUX. Any transceiver output fiber can be connected to any of the inputs of the colorless MUX. The aggregated output was then plugged into the input port of the OSFP-LS, where the signals were amplified by a booster. A fiber spool of 50 kilometers was then connected to the OSFP-LS output. The asymmetric front panel connectors of the OSFP-LS avoid any possible error to identify properly the signal ports and distinguish them from the fiber ports during the installation. The signals are then closed in a loopback configuration and then come back to the same 400ZR transceivers. The link is up, as you can see, from the green LED switched on the equipment. Now a second spool of 50 kilometer fiber is added. The original fiber is disconnected from the OSFP, and in fact, the LED that were previously green are now switched off. The second fiber spool is connected and the loopback is restored. After a few seconds, the link is back up again, and the green lights are clearly visible. I can show you a brief extract of the demo video itself.
Let's try to push it a little bit harder now. Let's try to go from 50 to 100 kilometers. And to do so, I'm gonna be connecting all this spool to this one. So I'm gonna be disconnecting first the setup. As you can see, the green LEDs will go dark. Okay, let me disconnect it now. Okay, I'm gonna take this fiber and connect it to this other spool. And now the output of this next spool for a total of 100 kilometers. I'm gonna put it back into the preamplifier input and let's see what happens. So it's going to take a few seconds for all the ZRs to lock. So as you can see, the LEDs are coming back up. And now all 8 LEDs are up. We're going through 100 kilometers with 8 waves of 400 XZR and the OSFP LS.
And now, let's take a look inside Poles. This innovative platform is enabled by 2.6 high-performance miniaturized optical components, including a 3-pin micropump uncooled laser for the amplifiers, which fits perfectly in the OSFP mechanical box. A very compact integration platform already proven, for instance, to build miniature erbium amplifiers for CFP2 transceivers. Smart and miniaturized passive components are a key building block as well. Hybrid and multifunction components, or single-sided devices, enable significant space savings and fiber routing in the package. And finally, a smart amplification control system enabling plug-and-play operation. Poles actually leverages the continuous innovation we've been developing in 2.6 with state-of-the-art passive and active optical components. Just a few words about auto configuration. Manual configuration is one of the problems that the IT guys feel could be an issue to be solved because it limits workforce productivity and can lead to installation errors. Poles is able to autonomously find the right settings to optimize the output power and the profile, to promptly adapt to input changes such as the increase or decrease of channels, or to line changes, for example, installing on a longer span versus a shorter one. Moreover, it also takes care of laser safety. The internal amplifiers will not be switched on if the fiber link is not verified closed, and they will be automatically turned off in case the fiber is disconnected or cut. Let's finally come to one of the most sensitive characteristics in a DC implementation, and that's cost. Considering a standard case of 16 channels, 16 400ZR channels, and the current OSFP configuration, 2 poles will be needed that have to be compared with a traditional full-line system, which includes likely a rack, a mux-demux unit, a preamp, and a booster amplifier at each edge of the link. Based on our experience, we expect a 3x savings on CapEx, and we can include other benefits. For example, less rack space, reduced power consumption, since you don't have multiple racks with multiple power supplies, and you save time in operations. We can quantify all these advantages and arrive to an overall cost savings of about 5x, depending on the specific customer equipment. To conclude, here you can see a summary of all the advantages that poles can bring to your DCI system. We think it can really make the difference as an ideal solution to reduce CapEx and OpEx for internet service and cloud providers and provide a best-in-class optical transport system for next-generation data center networks. So what can I say? Join us on the road to a poles revolution. Thank you for watching,